cut section method. So we have to decide where we want to cut. After that, when you cut, then you have to go step by step. In each cut, you repeat the process, show the positive shear, positive axial force, positive bending moment following the sign convention. Then you use equilibrium equations, then you get the axial force, shear force, and bending moment. So the step is the same. Only thing is now the direction of shear force, direction of axial force for each of the member, you must be clear. That's why I start with the definition of the directions of the shear force, axial force, and also bending moment. Okay? So that is the things that I would like you to be clear about. So checking of statical determinacy. So these are the way we check. You can cut. Then how many internal forces? 1, 2, 3. How many reaction forces? There are 3. So unknown forces, there are 6. Equilibrium equation, there are 2 parts. 2 multiplied with 3, you get 6. So this is statically determinate. You can also check in this way, simpler way. When there is no loop, you don't have to cut. So you have 3 reaction forces, 3 equilibrium equations. So alpha equal to beta. So this is statically determinate frame. Okay, class? So the next thing is you calculate the reaction force. So this is the same thing. Yeah, the first step, you have to calculate the reaction force, and you have to calculate it correctly, the reaction force, because later it will affect your shear force and your axial force and also your bending moment. So reaction force must be calculated correctly. So this is the first step, similar to beam. The second thing is we have to decide how many cut that we have to do. So that is similar to the case of beam. Only thing in frame, you have members like this, member like this, member like this. So how many cut? We are going to use the cut section method. So how many cut? So get the reaction force. This one is easy. Okay, this is the calculation. So you should try to follow this and try to confirm that this is the reaction forces that we will get for this example. So this is just applied equilibrium equations. So after this, then we have to decide how many cuts that we want to do. Okay. So here, basically the principle is that you should follow is, the guideline that you should follow is each of the member you have to cut at least once. Each of the member here you have to cut at least once. And if along the member there are changing in loading, then you have to do more than one cut. So here in this example, AB you cut once, BC you cut once, and then CD you cut once. So this is similar to beam. Only thing that beam, you only horizontal member. Frame, you have vertical, horizontal, and vertical again. So the cutting, where to cut. So cut, then the internal force will appear. Then we calculate the axial force, shear force, and bending moment. Okay, so how many cut you have to do is depends on the loading. So each member in the frame you have to cut once. Then if along each of the member there are some changes in loading, you have to do more than one cut. Okay. So here, class, I show you after you cut, then if you draw the free body diagram in order to get the axial force, we use the symbol Q. We use the symbol Q. Shear force, we use the symbol S. Sometimes we can use V. Then bending moment, we use the symbol M. So these shown here are the positive directions of the shear force, axial force, and bending moment. If you cut here and you use free body diagram of this part, and shown here is the positive direction of axial force, shear force, and bending moment. If you cut here and you use a free body diagram of this part, and here is the positive direction for axial force, shear force, and bending moment. Okay. So these are the positive direction for axial force, shear force, and bending moment that we have to draw correctly. Okay. Now, how to draw this? Okay, how to draw this? I will make use of this to explain how to draw this. So now here I show you again the same example. This one is not in your notes. After that, I will after the class I will upload on e-learning so that you can have. You pay attention first. If you look at this here, I show to you the same example, and then how do we cut AA, the first diagram here. This is where we cut here, and you separate into two. Then you cut here, you separate into two. Then you cut here, you separate the frame into two parts, the black part and the red part. So you separate into two. So the sign, the positive sign that is shown here as QSM, QS and M, QS and M is referring to if you use the free body diagram, after you cut this, you use this part, you use this part, and you use this part. Okay, so that is a positive directions for axial force Q, shear force S, and bending moment M. So that one is the free body diagram that we use is the black one. Yeah, the black one. That's why if you use the black one, then the positive direction is defined as shown in the diagram here. Okay. Now, sometimes we can use the free body diagram of the red part also for the calculation of axial force Q, shear force S, and bending moment M. If we do that, then the positive directions that we should use, if you use the free body diagram, the red part now, not the black part, then the positive direction for Q, S, and M is opposite to the one that is shown here. See, these are all opposite. And this is opposite to this now, and this one is opposite to this, and this one is opposite to this. So it is important for you to know how to draw the positive direction for axial force, positive direction for shear force, and then positive direction for bending moment. Okay. So I emphasize again, the one that we use in the example here is referring to you're using the free body diagram. You start from here, you cut, you use this part, you cut, you use this part. Okay. You cut here, you use this part, you cut here, you use this part, you cut here, you use this part. Okay. So that is the free body diagram that we are going to use. If you use the red one, then the positive direction should be opposite to this. So that is, okay. Now let's come back to this here. Come back to this here now. Cannot come back. Okay. Can, okay. So the next step is we have to cut, use a free body diagram, and then repeat to the next cut, and then the next cut, and then get the Q, S, and M. Here, I want you to pay attention to the direction now of this Q, axial force, S, shear force. So Q is always parallel to the axis of the member. Q is always parallel to the axis of the member. This is Q, this is Q, this is Q. S is always perpendicular to the axis of the member. S, shear force, shear force, shear force. It's always perpendicular to the axis of the member, and then bending moment is defined accordingly. Okay. So now we go to the steps involved. So this is the cut that we do here, and this is a free body diagram that we draw. This is a free body diagram that we draw. Now we put the axis X and Y here. We put the axis X and Y. This is to get the equations of bending moment for member AB. Okay, class? For member AB. Then you cut here, the free body diagram that you use is this part. And the positive axial force, positive bending moment. Axial force, we don't draw here yet because if you draw too many, too congested. So we forget about axial force first. Then we try to get the equation for axial shear force and bending moment first. So now, when you want to get shear force, you use equilibrium equations in the direction of the shear force. Here it is in the x directions. So you use these equilibrium equations. Then from this free body diagram, you can get shear force is constant along this member 10 kilonewton. Then the same thing, if you want to get the bending moment, then you take moment at the cut section. So this is the next step. Yeah, you take moment at the cut section similar to the case of beam. The moment is equal to 10 multiplied with x. So this is a straight line, 10 kilonewton. So x is changing from, for this member, 0 to 10. Okay, it's for member AB. So these are the set of equations for shear force S and bending moment M for member AB. Okay. So now if we try to draw this first for this part, okay, so this is the axis of the member. This is axis of the member, shear is constant. Bending moment is a straight line. So you put x is equal to 0, you get this value, x is equal to 10, you get 100 positive, so you draw a straight line. Okay, you draw a straight line. So this is for this part. For this part only, for this member, this is the variation of axial force and bending moment. So now we know if shear force is constant, then bending moment will be straight line. If shear force is straight line, bending moment is curve. So this is the same thing that happens in beam as well. This is constant, so axial force is constant, your bending moment will be a straight line. So next we move to the next section, so repeat the same process. So for this member BC now, try to get the equation for member BC now. So you cut here, then you use the free body diagram. This is a free body diagram that we use. This will be the free body diagram. Then the positive S, positive bending moment, is as indicated here. Then our X and Y here now. So X and Y, this is X and this is Y. Okay, look at the X and Y. So you use equilibrium equations in the direction following the shear force. This is Y now. For member AB, for member BC is Y now. So that's why we use these equilibrium equations. Then we consider all the forces in the direction of shear force S, which is Y. Then we get S is equal to S minus 15 plus phi x equal to 0. Okay. Phi x has come from here. 15 is coming from here. Okay. So S become 15 minus phi x. So that is a straight line. So shear is a straight line now for BC because there is a distributed load there, UDL. So next class, bending moment. So bending moment, the same thing. You take section, take moment at the cut section here. Then you get moment, yeah, this bending moment plus this is due to this load. And this one is coming from this. And this one and this forms a couple, 10 multiplied with 10 and directions opposite to this. So you have negative 10 multiplied with 10. So summarize, if you simplify it, you get M is equal to negative 2.5x squared plus 15x plus 100. So shear is x, then bending moment will be x squared here. And again, the x is from 0 to 10 because it's for this member, 0 to 10. So now if you try to draw this part using this equation and these equations for this part only, now you are going to get this represent member BC, this represent member BC. So the shear force is a straight line. The shear force variation is a straight line for member BC. And for bending moment is a curve, parabolic curve. It's a parabolic curve. And because we have minus here, minus x squared here, so it is curving in this way. Or you can get the relationship between the slope in bending moment diagram is equal to the shear force. So shear force is changing from positive, then becomes 0 at B prime, then changing negatively. So the slope will be positive, 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 and then 0 slope at B, then change to negative slope. Follow the shear force diagram. Now here, whenever we have a 0 shear, whenever we have a 0 shear, there's a 0 shear point here. Okay. You have a 0 shear here, so you have to calculate. You have to calculate what is the location, so you get the maximum bending moment. So you have to calculate this. You have to calculate this distance here, because we want to get what is the maximum bending moment. So how to calculate? We make use of shear force at this section minus shear force at this section is equal to area under the loading diagram, which is this is going down, so minus 5 multiplied with this distance, if the one that we want to calculate. So from here we can get this is 3 meters. So this is using what we have learned, the relationship between shear force at one section minus shear force at the other section, then equal to area under the loading diagram. Then we can determine this distance. So this one substitute into these equations here, then we get the maximum value there. Because whenever there is a shear 0, you will have like this, or somewhere maybe happen down there, a maximum point or a minimum point. And you have to indicate what is the value there. So to indicate this, you need to know where does it happen here. So this is to calculate where does it happen here. Okay. So after this, you have the last part. We have a last part that we have to draw. So here, again, we just make use of the relationship of slope in bending moment diagram is equal to the shear force at the same point. So positive shear at B, so the slope is positive, then slowly decreasing to 0 at B prime. So that's why you have a maximum point. Then after that, B prime, you get shear negative all the way increasing, so your slope all the way negative increasing. That's why we get this shape here. That's why we get this shape. So class, is very useful to remember these so that you can confirm what should be the shape of the bending moment diagram for this part. Okay. Let me check who is. Okay. So now we go to the next one. Okay. We go to the last part, which is here. Okay. So again, you cut there. This is a free body diagram that we use. Then the positive shear and the positive bending moment that we get here. Positive shear, positive bending moment. If we use this free body diagram after we cut here. Positive shear, positive bending moment. Then here, shear is in the direction of x-axis now. It's in the direction of x-axis now, so you make use of that equilibrium equations. So in frame example class, direction of shear force sometimes is y, sometimes is x. So you make use of the corresponding equilibrium equation of forces in that direction, similar, parallel to the S at the cut section that we are looking at. So in this case is summation of forces in x directions. Yeah, so S plus 10 here, this is a 10 here. So minus 10, another 10 here. So S becomes 0. S becomes 0 means in that member there is no shear force. That member there is no shear force. Then repeat for bending moment. Yeah, for bending moment, if you take moment at the cut sections, so this will be the equations involved. So here is, you must be familiar now how to consider moment caused by different type of forces. Okay, this is what we have learned. So you have to familiar now how to consider moment caused by different forces at section XX, section here. So these are the moment and then make them equal to 0. So you find M, all this also 0. So M also 0. Okay, meaning that that member has no bending moment and no shear force acting in the member. Now, we have an options. When you cut here, you have two free body diagram. Here, just now we use this one. And these are the positive axial, positive shear, and positive bending moment. We can also use the other part, which is simpler. The free body diagram becomes simpler, but the positive direction now is axial force, shear force, and bending moment in this way. Then this is a free body diagram. That will be the free body diagram. And then from there, you see S equal to 0, M equal to 0. So the calculation is simpler if you use this part here. Because use this part, you have to consider more loading here. But use this part, it is only this. So this only cause axial force. It doesn't cause shear. It doesn't cause bending moment. So immediately we see this is 0 and 0, which is the same as the result that we calculate using this part. So if we realize that this case is better to use this part, but then you have to indicate correctly the shear positive and axial positive and bending moment positive, which is opposite to this direction if we use free body diagram of this part here. Okay. So if it is S shear force 0, bending moment 0, so when we draw the shear force diagram, it is just like this 0. Okay, 0, no value there. Okay. So now if we combine all, so this is the finally the shear force diagram. Yeah, we have to show this. Okay, we have to show finally shear force diagram that for the whole frame. Just now in the solution process, we show part by part. Now we have to combine all. Okay. So here constant, then here straight line, here 0. And here in this diagram here, you see the axis. This is for plotting. Yeah? This is the axis of the member, axis of the member, axis of the member. Then this is x-axis, y-axis. This is for plotting this part. This is x-axis, y-axis for plotting here. And this is x-axis, y-axis for plotting the diagram on this member. Okay? So this is like you plot the graph. Okay, we plotting the graph. X, Y, X, Y, and then X, Y. So positive you plot here, negative we plot here, positive we will plot here, negative will be here, positive will be here, negative will be there. So this is the meaning of this red arrow here, okay, for X and Y axis. Then for bending moment diagram, this is the bending moment diagram for this frame. For A to B, you have constant. A is simply supported, so moment 0. From B to C, there is a uniformly distributed load, so it is a curve. Then there is a shear 0 point here. That's why we have a maximum bending moment, 0 here. And then this member all 0. So next is the axial force. Okay, just now axial force we don't show in the free body diagram, because if you draw a free body diagram, too many axial force, shear force, bending moment, then too many things there. So we omit first the axial force. So finally we calculate the axial force. So axial force is shown here. The first part for AB. So we cut. Then this is the positive axial force. Then from here, we take the equilibrium equation, follow the axial force direction, which is Y. Then we get Q negative. So Q negative means the correct direction for shear force Q is going down, which means that member is in compression. We assume tension, but that member actually is in compression. The correct direction is going down, which is pressing this member, means that member is in compression. So next one, okay, this is for part AB. So if you draw for AB, it will be like this. Negative, so positive we draw here. So negative on this part, we draw on this side. So constant all the way. So this is the axial force diagram for part AB. Okay, for part AB. Then for this part here, we have to get also the axial force. So we for this part, class, if you cut here, then you make use of this free body diagram. So this is what we get. Positive axial force. So from here, this is in X direction. Now, just now in Y direction, this is in X directions. So if you take equilibrium equation in X direction, then you find that Q is equal to 0. Q0 means that member has no axial force. They have no axial force. And then finally, the last one here. The last one here. The last one here now, we cut here. We cut here, but we don't use this part. Okay. We cut here, but we don't use this part, but we use this part only, which is this free body diagram here. Cut here, but then you don't use this part. You don't use this part, but you use this part only. So you get Q is equal to negative 35. From here, you make use of the equilibrium equation in Y direction, that you get Q is equal to negative 35, meaning that it is also in compression. We assume in tension, but the actual force in that member is actually in compression. So we draw here, okay? So this is the actual force diagram for AB, negative 15. For BC is 0. For CD is negative 35. So for this member, if positive, we draw here. Negative, we draw on this side. So it becomes negative 35. That's why the diagram comes to this part there. So that is the axial force diagram for this frame, or sometimes we call it the truss diagram. So that complete the shear force diagram, axial force diagram, and also bending moment diagram that we want to draw. Now, we draw the qualitative deflected shape. So class qualitative deflected shape, you have to remember it is based on bending moment diagram. Then you have to know this is supported and this is a roller. Roller means it can move like this, but it cannot move up and down. So pin, it cannot move left and right, it cannot move up and down. Then this is the bending moment diagram, and bending moment diagram is drawn on the compression side. Bending moment diagram is drawn on the compression side. So we know which part of the member should be in compression. If we know which part of the member should be in compression, then we should know how it should bend. Okay? This part is in compression, so how it should bend. This part is in compression, top part, how this member should bend. There's no moment. No moment means this member must be straight. It cannot bend. No moment means it will not bend. It will remain straight. Okay? It might move, rotate, but it must remain straight. And this point can move, this point cannot move. So that is the point that you have to consider when drawing qualitative deflected shape. So this is compression on this side. compression on the top part, no bending. So qualitative deflected shape, our qualitative deflected shape will be like this. Okay. This one should bend like this so that this side is in compression. This side should bend down so that the top part is in compression. And this one here, you see, it should remain straight because there is no bending moment. Okay. And the other thing is in frame, this angle here and this angle must be maintained. The angle here and angle here must maintain 90 degrees. After you deform, it must also maintain 90 degrees. Here, 90 degrees must maintain 90 degrees. So those are the points that we have to take note when we sketch this qualitative deflected shape, which is based on bending moment diagram, and also take note of the support conditions. And this bending moment diagram class is drawn on the compression side. Drawn on the compression side. So this is the qualitative deflected shape for this frame. So I show you here also the when it is compression, meaning that how it should bend. Okay. Compression on this side, it should bend like this for that member. And for this member, the top part is in compression so that it should bend in this way. Now, I want to talk about this, where to draw the shear force diagram and bending moment diagram. Then we will take a short break. Okay. Where to draw, okay? In beam is simple, where we have x-axis, x represent the axis of the beam, positive you draw on the top, negative you draw at the bottom. But here you have frame, vertical member, horizontal member, and sometimes inclined member, and then, so where do we draw the shear force if it is positive, negative? So here, the first thing that we need to know is we should know the axis of the member. So we start from this left-hand side. So this is axis from A to B. This is the x-axis. And the one which is perpendicular to this will become the y-axis. This is x and this become y. Okay? X and y. Then if you go to here, so this become the x and that become the y. So this is like xy plot, another xy plot for this member. When you come here, if this is x, then y going this way. So you have another xy axis where you should know where to plot for positive, where do you plot for the negative one. Okay? So that is the next thing that I want to share, where to draw. So this is this particular slide, when there is some beautiful hand drawing, always become like that. Okay. Now, where to draw is yeah. You have to decide the x-axis first for the member, starting from this left-hand side, x-axis of the member, and then the one perpendicular to this x, y. Okay, this one is x, this one is y. So then the one which is positive, you draw here, negative, you draw on this side. Positive, you draw here, negative, it becomes at the bottom here. So that is where we should draw. Okay, class? And I show here as well the green, the blue arrow here is the positive direction for axial force, positive direction for shear force, and positive direction for bending moment. The same thing here. So this is where we plot. Positive plot here, negative you plot here, positive here, negative here. But this is based on the positive direction, and positive direction for the axial force, shear force, and bending moment. Axial force, shear force, bending moment. Okay. This is the red one, indicate where to plot. This one indicate the positive direction for the axial force, shear force, and bending moment. So same thing. Okay. Okay. This is the where do we plot, and the corresponding positive direction for axial, shear, and bending moment. So if we get this is if we get a problem like this, then this is the axis of where we should plot positive and negative shear, positive and negative axial force, or positive and negative bending moment. So we start from the left end and then we go. You make a series of this XY axis. So this is XY, 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 and XY there. So when you come to here, positive, you plot here, negative here, positive here, negative here. So this is the axis for plotting. Then the corresponding positive direction for Q, S, and M is like this. Okay. This is the corresponding positive directions. Now I know why it become like this, because this doesn't like this artist to draw something like this here. So you use Microsoft this draw function, then no problem. When here suddenly like this, so doesn't want you to see this drawing here. This is I don't know who is the artist to draw something like that. There, you see what happened? This. Okay, so this is showing your positive direction, but this is if you cut here, you use this part. If you cut here, use this part. If you cut here, you use this part, and the same thing. So that is the free body diagram. To the left of the cut section are being used. Then that is the positive directions. If you use the other side, then remember the positive direction become opposite to what I show here on this slide. And if you get positive moment, that is how, if you want to draw the qualitative deflected shape, if you get positive bending moment, that is how each of the part is going to bend. If positive bending moment means it will bend for this member, bend like this, compression here. Positive you draw here means compression side here. Positive you draw here means compression side, so bend like this. The same thing for here and here. So this is how the member will bend if the moment is positive. If the bending moment is negative, then it will bend the other way. It will bend the other way around. So this is to relate to you. If it is positive bending moment, you draw on this side. If you draw on this side, means your bending moment is drawn on the compression side. Compression side means this part. Compression means the beam will bend in this way. Okay. So now we are 70 over 149. Okay. Now is 9:35. I want to target to finish by 10:29. Mission impossible. Okay. Mission. We try to make it possible. Any question, class? I didn't expect that. Sorry about the pink color of this thing. Okay. Any questions so far? Please refer to your notes. Huh? I hope you bring the notes, I think. Have you been able to access eLearn? Able to get? Can you find these notes? Before, during my time, we go to lecture, we bring papers, lecture notes. I think now have that. Huh? You have share. You share, right? Okay. And here you from the smartphone can see, huh? Have, right? Smartphone no battery then now. So class, I think I have go through with you one example very detailed. So we are going to go through few more examples just to get you more familiar with the process. So you can see it is very similar to the case of beam. You get reaction force, you cut, then you draw free body diagram. The only thing frame, shear force, sometime like this, depending on the member. So you have to know how do you define shear and axial force. Because when you want to use equilibrium equation, you have to follow direction of the shear force, direction of the axial force. This is especially later we see inclined member. Inclined member, then the shear force and axial force has to be defined correctly. And after that, the equilibrium equation that you are going to use will follow direction of the axial force, direction of the shear force. So that's why it's important to get to know the definitions. How do we define shear, axial, and bending moment? Okay? So it is always defined on the section perpendicular to the axis of the member. So you see axial force changing. Yeah, axial force direction changing. Shear force also changing. So when we go to more example, then you try to get yourself familiar with the direction of axial force, shear force. Bending moment is easier to relate to because bending moment is, we all define this counterclockwise, 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 counterclockwise. This is counterclockwise, counterclockwise. But it's axial force and shear force which makes the calculations, I think, a bit lengthy. It is not difficult, but the calculation become very long because of the changing directions. Now let me check one online. Okay.